We're gonna have the rain on weekends. The whole weekend gonna be raining. So, as I promised you, we are now to Roth, Horowitz, stability criteria. So, you know that we can have nth order system and the closed transfer function x y over x. I'm just writing here 1 for now. Can be nth order system like as an Sn plus an minus 1 Sn minus 1 plus an minus 2 Sn minus 2 plus an minus 3 Sn minus 3 and plus a 1s plus a naught. And n can be any number. It can be 10th order system, can be, I don't know, 154, can be any number, depend on the system. So Roth stability criteria says, Roth stability criteria help us to judge system stability or even marginally stability, marginal stability or instability of a system given and also determining number of right hand poles of the system if any, and also I'm changing the color because it's very important. It's going to help us in designing controller PID, and also determine the range of stability for system parameters. Parameters. So it's a stability and instability tool that help us also to design controllers after midterm, after the spring break. So this, when your system order is n, how many poles you're gonna have? Because from high school, you're gonna have n poles, right? N poles. But sometimes, in rare cases these days, you have no access to computer to go to MATLAB or your calculator and calculate the poles of the system. And more importantly, your system coefficients are based on parameters, not the numbers. And you want to know for which range of parameters your system is stable and which and it's unstable. And based on that, you design your controller. So how we do that? Can I go to the next page? Yes? Okay. First condition that system is stable is all coefficients exist and must be positive. Must be positive. This is first condition of the stability in a system. Must be positive and exist. Means an, these coefficients, an minus 1, a minus 2, a naught, a1, an minus 1 until an non-zero exist and must be positive. If any of these coefficients missing, your system is not stable. Can be marginally stable, can be unstable. For example, now I'm taking you back to the first class of this course that you had with me. This is the closed transfer function of pendulum. Omega n square s square plus omega n square. Is this system stable? Huh? Are we missing any coefficients? Just look at it. This is not magic. You have to use your eyes. Are we missing any coefficients? Yes. What is that? Yes. We are missing s. 0s plus omega n squared. So bingo, the system is not stable. And I showed you, system here is marginally stable, oscillating forever. And as you know, you have a pair of pure imaginary poles, I omega n. See here, by solving this. If you plot in the complex plane, real, imaginary. So we had these poles here on the imaginary axis. So only by looking at this you can judge it now. It doesn't satisfy the first condition. Or if you have this system, for example, you have a closed transfer function y over x is 1 over s cubed plus s squared plus 2s minus 1. Is this system stable? Without even solving it. Stable or unstable? Huh? Yes, because of what? Yes, one of the coefficients are negative. All of them must be positive. So this is the red flag. Saying, oops, you as a control engineer, you are in danger of instability. This can be your car and gonna make you die when you drive. This can be airplane. This can be robot. This can be the room temperature. This can be tank of water. This can be pressure of a tank. This can be whatever that you are controlling. This can be shuttle, space shuttle of the Elon Musk. Okay, so you as control engineer, you see, oh, I don't know what's happening today with this PowerPoint. Okay, I have a danger here. And you have to design a controller to fix this. And we're gonna do that together after. And we're gonna use this Roth-Horowitz to design controller. Okay. But this is the first condition. The second condition, I have to go to the next page. The second condition is this. You have to make a table. Table is this. Sn minus 1, Sn minus 2, and coming down, S naught means the constant. S naught means constant. Then you have to go here and say, okay, Sn, you have to select like this. this 1/3, 5th, 7th, like this. So we're gonna put here an. The next one is an minus 2. This subtraction odd. An minus 4, an minus 6, 0, 2, 4, 6. Now the first one is this. I'm just changing the color. An minus 1, an minus 3, and n minus 5 goes like that. Okay. Oh my God. Okay. So you have to write like this. An minus 1, an minus 3. So these are evens, these are odds. An minus 5, an minus 7. And as long as continues, you have to continue. Okay. So the first two rows you're gonna make from the closed loop transfer function coefficients like this. Last row, there we go. Last row, you don't have to just do it. You have to put this constant a naught here from here. Just copy it. A naught. Because the coefficient of S naught, constant number. Now here, what you're gonna do is a rule. Here, you're gonna say this multiplied by this minus this multiplied by this divided by the first one. So here you're gonna say an minus 1, an minus 2 minus an minus 3 divided by an minus 1. Next element, this multiplied by this minus this multiplied by this again divided by this. So it's gonna be an minus 1, an minus 4 minus an minus 5 divided by an minus 1. The next one, this multiplied again by this minus this multiplied by this divided by first one. An minus 1, an minus 6, a minus an minus 7 divided by an minus 1. And continues as long as it continues. You got it? Next line. I'm just doing here for example, huh? Let's put Sn minus 3. What you're gonna do is the same. Let me call this as A. Do you mind? Let me call this, let me change the color. Yeah, let me call this as A. And call this as B to avoid repeating as B. A multiplied by this minus B multiplied by this divided by A. So you're gonna have an minus 3 minus B an minus 1 divided by A. Now again, A multiplied by this, sorry, A divided by n minus 5. Gonna be an minus 5. That's right. And now let me call this as C. And minus C multiplied by an minus y divided by again by A. And continues. And you have to make this table until the last line that is here. When you make that, I'm going to delete these things because I want to make a point. Okay, when you make that, you're going to have the first column. I'm going to circle it. You have a first column in this table. This first column. Here we go. Second condition, the first column of table must, oh my god, so I don't know what's wrong with this guy. It's just hold on. Maybe. Just let me. The first column of the table must exist, means non-zero, and like previous case, be positive. Number, this is very important. Let me change the color. Number of sign change in the, can I go to the next page? Guys, can I? In the first column indicates the number of right hand poles. This is very interesting. Right hand side poles. Right hand side poles. Why this is important? Because now you know it. I taught you, if this is the complex plane, real, imaginary, this side is unstable, right hand side. This side, the left hand, is stable, and this is margin stable. That's right. So it shows that how many poles we have there to fix it by controller. Now let's go eventually by examples. Simplest one that I derived with you. Suppose that y over x is equal to 1 divided by s squared plus 3s plus 9. So what you're going to do, first check. All exist and positive. Bingo. Second one, you're going to make this s squared, s1, s0. So it's going to be 1, 9, as I told you. And then 3, here is 0. We have nothing. Last line, I told you take from where? From this constant, 9. All first column exists and positive. Your system is stable, and it is. This is under damped system, guys. You have a pair of complex conjugate poles. Because poles of the system, you know that is equal to -3 plus minus 9 minus 36 divided by 2. Gonna be -3 plus minus I 27 divided by 2. A pair of complex conjugate poles. It's here. But by rule of stability criteria, we can just, without going for the solution. Let's go for a little more higher orders. Can I go to the next page? Yes? So y over x closed loop transfer function, suppose this is 1 divided by s cubed plus 2s squared. This is very random I'm writing, okay? And 1s plus 5 plus 5. First check, all exist and positive. Bingo. Second check, you're gonna make a table. S cubed, s squared, s1, s0. Now you know the rule. The last line, bingo, 5. 5. Here, s cubed, 1, 1. Second line, 2, and 5. See? 1 and 1, 2 and 5. Now this multiplied by this based on the formula minus this multiplied by this divided by 2. Gonna be 2 minus 5 divided by 2. Oops! Is minus 1.5. It says your system is unstable because this is positive, but this is negative. Now let me guess that how many right-hand side poles you have. I said, based on definitions, number of sign change in the first column indicates the number of right-hand side poles. Look at here, guys. From positive 2 to negative 1 sign change. From negative to positive 2 sign change. You have 2 right-hand side poles. This is very bad. Your system is unstable. So let me take you to the MATLAB and show its proof. Okay. MATLAB. You saw that Roll's disability told us that you have 2 right-hand side poles. And I'm going to solve this. I'm going to show you. See that how powerful is this? 1, 1, 2, 5. We did it. 2 minus 5 divided by 2. Minus 1.5. Come on. Until this comes up, let me give you another example. Oh, it came up. Okay. So, see, I'm going to say, come on. I'm going to say, solve this from high school. Now you know how you do Sims. Come on, don't be. Sims X, I'm defining as symbolic. So, you know, A is okay. A is double or double works better. Double solve, and what's the equation? 1, 2, 1, 5. So x cubed 2x squared 1, 2, 1, 5 plus x plus 5. So you see, guys, you have a pair of complex conjugate poles on the right hand side plus 0.16, and this is what in the right. So you see, you have a pair of complex conjugate poles on the right hand side. So your system is very unstable, guys. So you as control engineer, you have to fix it. Let me plot it here. So this says even without using MATLAB, your system closed loop transfer function had 3 poles, because 3 was this. and this is very dangerous and make your system unstable. And what's the function? Design a controller to push this to the left hand side. You got it, everybody? Now let's go to say fifth order. If system can be fifth order, can be say S5 plus 2S4 plus 10S3 plus 2S square plus 4S plus 10. First, check all exist and positive. Bingo. Second, we're gonna make table S5, S4, S cube, S square, S1, S naught. We know the last line we are copying from here. 10. First line, S5, S cube. This is gonna, you have to write here. Gonna be 1, 10, and 4. 1, 10, and 4. So S4, we're gonna again take from here. Change the color. 2, 2, 10. So gonna be 2, 2, 10. Now we're gonna make it 20 minus 2, 18, divided by 2, 9. 20 minus 2 is 18 divided by 2, 9. 8 minus 10, oops. 8 minus 10 is how much? Minus 2. Divided by 2 gonna be minus 1. We don't have to that, we're gonna stop it here. See, 8 minus 10 divided by 2. Minus 2 divided by 1 is minus 1. Now this line. 18 plus 2, 20 divided by 9. Gonna be how much? 18 plus 2, 20 divided by 9. 20 divided by 9, positive. 90 minus, here is 0. 90 divided by 9, gonna be 10. Here we go. 90 minus 0 divided by 9. It's gonna be, now this line. This multiplied by this minus this multiplied by this divided by this. Gonna be 20 divided by 9 minus plus 90 divided by 20 divided by 9. Right? It's gonna be a positive number, obviously, because this is very small. Right? Oh, I'm sorry, guys. Actually, it's not. A minus, and this is minus. I'm sorry. And divided by this. It's gonna be obviously a negative number. Let me say this as A. A. So now let us pick the first column. Positive, 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 negative. Your system is unstable. How many right-hand side poles you have? From plus to minus, minus to plus. You have 2 right-hand side poles. Your system is unstable. You have to fix it. Proof? Let me show you my MATLAB. So, seems X is this. So, can you read the coefficients of, let me, S5 is 1. What is X4 coefficients? Can you read for me? 2, X3, 10 multiplied x2 to x1, and finally that's 10, that's right. Oops, again, two right hand side poles. The rest is real pole, a pair of conjugate poles on the left hand side, but a pair of complex conjugate poles on the right hand side. See, positive point. So the system is unstable, as the Roth stability criteria says, and you as control engineer, after the midterm, based on the design and control, you have to fix it, and the companies, they're gonna pay you. So if this is complex plane, imaginary, real point. So it has like this 2 here and here. These are good. You have danger here on unstables. You got it, everybody? Yes. Now, suppose we have some special cases. Special cases. 1. If in the first column of table that you made, one row, only one, not row, one element is 0 and there is no sign change above and under that, you have to replace that 0 with positive epsilon, a small number, and then do the analysis. Okay? Let me take you this. Y over x, I'm going to take you to the simplest one. To the pendulum, the first class of this course. Obviously, we are missing s. Okay? But if you want to make this table, because this is like this, remember? S squared plus 0s plus omega n squared. So it's going to be 1 omega n squared. Here is 0. And then the last line, you know, is constant. It's natural frequency squared. Obviously, this is positive. And this is positive. Okay? You can replace it with epsilon plus. You're going to tell me what's the point. This is very trivial. I just want to show you. Okay? But did you see that above, first of all, above and under that, because I'm going to teach you on the designing PID controller based on exactly this. Above this is positive and below this is positive. This shows that your system is marginally stable. Exactly, we're going to use this in designing PID controllers from this table. Marginally stable. It's positive, positive. Okay, this is one point. Now let me take you to a complicated example. So y over x. Oh, are you done with here? Huh? Are you done? Okay. So it says, let me think about this, okay? S cubed plus s squared plus s plus. Because I have no notes, I have to think about this to make this one of them. Okay. 1, 3, 5. Okay. 1. I'm gonna make it the fourth order system. Actually, you know what? No, I'm gonna keep it third order system. And 3, 3. So you see, 1, 3, 1, 3, 1, 3, 1, 3. The last line is I'm copying from here. 3. Okay. This is not good. I have to make it fourth because I want to make a point. This is not good, guys. Don't do it. I want to say why we are doing that. Say S4, S cube, S square, S1, and plus a constant number. S4, S cube, S square, S1, and S0. 1, 3, 5, 1, 3. This is good. So the coefficient is going to be 1, 3, 1, 3, and 5. Here we go. So you see that I copied from here. 1, 3, 5, the first line. Second line, as you know, is 1, 3, and 0. I just copied from here. That's right. And the last line is coming from 5. There we go. I just copied. Now here. Look at here, guys. And this is 0. 1 minus 3 minus 3, 0. Right? See, guys? 1 minus 1, 1, 5 is going to be 5 here. Right? See? 3 minus 3, 0 divided by 1, 0. 5 minus 0, 5 divided by 1 is 5. Now I want to go to this line. This line is going to be ridiculous. Because 0 minus 5 divided by 0. What's the meaning of this in the mathematics from high school? How much is this? How much is this? Infinity. Undefined. 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 So we're stuck here. We cannot judge anymore. We're stuck here. That's why I'm changing 0 with epsilon plus. Okay? A small number. So it's gonna be 3 epsilon plus minus 5 divided by epsilon plus. Now this is gonna be a negative number, obviously, because 3 epsilon plus minus 5 is a negative number. So I'm gonna say A is gonna be negative number. That's why we are changing 0 with epsilon plus. Make us to continue the process. Now looking at this, positive, 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 negative. Your system is unstable. one sign change, two sign change. You have two right hand side poles. You can examine that in the MATLAB. Okay, you got it? Yes, everybody? To make us, so if you have 0, you have to change it. Now, second special case. If a row in the table is 0, not only one element. For example, this row is 0. Oh, what the? For example, this row is 0. You stop. You have to get help from auxiliary polynomial. How? Example. Y over x is this. Let me think about this, okay? S6, S5, fixed order system, S4, S cube, S squared, S1. So when you make the table, S6, S5, S4, S cube, S squared, S1, S0. 1, 2, 1, 2, 2, 3. Then 1, there we go. So I'm gonna make this okay. Yeah. So it's gonna be 1 plus 2 plus 5, 1 plus 2 plus 5. Here we go. Fifth order system. So you see that 1, 2, 5, 1, 2, 5. Okay, we just made it. Next line. 2 minus 2 divided by 1, 0. 5 minus 5 divided by 1, 0. So you're stuck here. You cannot go ahead and one row is 0. What you're gonna do, you're gonna get auxiliary term polynomial P of S. You're gonna look at the line above that. You're gonna look at the line above that. This is how we do for any system. Line above the 0. So this one is from 4. You're gonna say S4. See, 1 coming from S4 and 2 coming from 2S squared plus 2S squared. You're gonna write like this because we got this one from S4 and these two from 2S squared. You're gonna make like this. Then you're gonna have the derivative with respect to S, dp over ds. This is the rule. Gonna be 4s cubed plus 4s. Oops. So you're gonna write here, okay? You're gonna put the coefficients here, guys. Gonna be 4 and 4. You're gonna put here. You got it? 4. Now you're gonna can continue. 8 minus 4 divided by 4. 4 divided by 4 is 1. See, 8 minus 4, 4 divided by 4 is 1. 20 minus 0 divided by 4 is 5. You're gonna put it here. Now, continue. 4 minus 20, how much is that? Minus 16. Oops! Negative number, guys. You know the last line coming from here, 5. Now, 16 by 5, how much is that? 16 by 5? Huh? Gonna be minus 80. Am I right? Minus 0 divided by minus 16. Gonna be how much? 5. That's right. 5. So it shows the first column is this. Positive, 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 positive. Oops, negative, positive, positive. 1 sign change, 2 sign change. You have 2 right hand side poles. So the lesson is if you have one row is 0, you get the auxiliary term polynomial from the upper line. Differentiate with respect to s, put the coefficients here and continue. You got it, everybody? Yes? It was, I wanted to go to higher order, but it was very complicated. I just stick to the 5. It was just example. Okay? Because I have no notes, you know that I'm teaching from my mind. Okay? So, and I hate to use notes. It shows that I'm not professor. Whatever I am, I'm not professor. If I teach a material for more than now 12 years, I cannot teach from my mind. Maybe I'm burger engineer, but not professor. Okay? So, S5, S cubed. So see, 1, again I'm repeating. 1, 2, 5. I'm just putting here. 1, second line. 2, 5, 0, 0. We put here 0. I mean 2 minus 2, 0, 0. 5 minus 5, 0. But we stop here. So we go to the upper line. This one comes from S4 and these two coming from S squared. Exactly like this here. We have a derivative with respect to s, gonna be 4s cubed plus 4s. These coefficients we got exactly put in here and continue. 8 minus 4, 4 divided by 1. This is gonna be 5. Continue. 4 minus 20 minus 16. Oh, negative. dangerous, and this gonna be positive. So for showing you the proof, this fifth order system in MATLAB. Can you read me the can you give me the coefficients? X5. Can you read, what is X4? What is X4? What is X4?
It's
1. What is X3? 2. What is X2? 5. 2. Okay. And here's 5 and 5. That's right. Yes. Okay. See, 3 left hand, 2 right hand. These are dangerous. A pair of complex functions on the right hand side. And they're gonna tell me payment. Okay, now these days MATLAB is here. Why we have to spend for the row stability criteria? Just we're gonna use the solve command in MATLAB because it gives us the poles and we know the system is stable or unstable. And you're right. This method is invented for I don't know 60s, 70s. Okay, computer was not developed. It was a powerful tool for that. But what I'm gonna cover the next class before midterm is if your system is this, and you are the designer of the controller after the midterm. Is the system is this S4 plus K1S3 plus K2 plus 2S squared plus K3S plus K, no, not K4 even, plus 5. You have a system that you are not certain after deriving differential equation of motion. You are not certain about the K1 and K2 and K3. These are the parameters of the system. Even adding the controller, I'm going to teach you, these can be the PID gains. Okay? So we want to see for which range of K1 and K2 and the K3 the system is stable or unstable. So we're going to do that next class, and I'm going to give you a hint about the midterm, and I'm going to give you some tools for the midterm about the linearization, and then you are fine. And just hold on a little before going.